Functions. Function notation is a way of writing equations of functions that shows us the input and output of the function. Instead of writing y equals 3x minus 1, we write f of x equals 3x minus 1. Here we can see that x is the input and f of x is the output. To evaluate a function in function notation, you have to substitute a number in for x and then simplify. For example, if f of x equals 3x minus 1 and you're asked to evaluate f of 4, then you would write f of 4 equals 3 times 4 minus 1 and find that f of 4 equals 11. When you're asked to find the domain of a function, you're being asked what values can be inputted into the function. If you're asked to find the practical domain, then you're being asked to find what values can be inputted into the function that make sense in the real world. Let's look at some examples. A rocket is launched from 180 feet above the ground at time t equals 0. The function that models this situation is given by h of t equals negative 16t squared plus 96t plus 180, where t is measured in seconds and h is the height above the ground measured in feet. What is the practical domain for t in this context, and why? Well, the rocket is being launched 180 feet above the ground, so right about here, and that starts off when t equals 0. So t is going to be equal to 0 at the beginning of our practical domain, and then the rocket goes up and then hits the ground. Now once it hits the ground, it's not going to keep going down into the ground, or if it did, it wouldn't go along the same path. So then we can say that the practical domain is when t is between 0 and 7.5. And the reason why is because we want to keep the height above the ground, so those are the times when the height is above the ground. Or I could also phrase that as the time when the rocket's height is being accurately measured. So accurately measured being it actually was at 180 feet at t equals 0, and then it was at 0 feet at t equals 7.5. So what is the height of the rocket 2 seconds after it's launched? Well, 2 seconds after it's launched, that would to figure that out, we'd say h of 2 equals negative 16 times 2 squared plus 96 times 2 plus 180. And we'll evaluate that and get that h of 2 equals 308. So it's 308 feet above the ground 2 seconds after it's launched. Alright, what is the maximum value of the function and what does it mean in the context? Well, in our problem, in our graph, we already have that the maximum value, so the height, is 324 feet, and that happens 3 seconds after it's launched. So if I didn't have this already on the graph, then I could of course graph it and create the graph. That's always an option, but there's also the formula negative b over 2a. And negative b over 2a gives you the axis of symmetry. And remember, axis of symmetry is this imaginary axis or line that goes right through the middle of your parabola and breaks it into two equal pieces. So negative b over 2a would give you that value. And then that would, of course, equal 3 for this particular problem. And then you would just plug the 3 in for h. So we'd find that h of 3, you'd solve that, and you'd get 324. So this is the height this is the height after 3 seconds, and it's the highest height that the rocket actually arrives at. To find when the rocket is 100 feet above the ground, then we're going to need to solve the equation 100 equals negative 16x squared plus 96x plus 180. Alright, to do this, what we would want to do is set this equation equal to 0. So I'll need to subtract 100 on both sides. And then we'll need to use the quadratic formula. So we have our quadratic formula, and we'll just plug in the pieces. So that'd be negative 96 plus or minus the square root of 96 squared minus 4 times negative 16 times 80 all over 2 times negative 16. And we'll simplify this to get x equals negative 0.74 and x equals 6.74. When is the rocket 250 feet above the ground? Alright, so I'm going to take the 250 feet, and since that's a height, I'm going to put that in for f of x. So I'll have 250 equals negative 16 x squared plus 96x plus 180. And I'm going to go ahead and get this set equal to 0 so we can solve it algebraically. So if you don't want to solve this algebraically, you could solve it graphically. And what that would require would be you would graph a line at 250 feet, so wherever that is up here, and then you'll find these intersection points of the line. So you can do this like a system of equations. Alright, but algebraically, I'm going to use the quadratic formula. So now that I have the quadratic formula, I'm going to do x equals negative 96 plus or minus the square root. Fix my plus or minus. And then it'll be b squared minus 4 times a times c all over 2a. And then I'll use my calculator to evaluate that. So x equals 0.849. These are rounded values, and x equals 5.15. So the rocket is 250 feet above the ground when, let's see, so the time would be 0.849 seconds after it was launched and 5.15 seconds after the rocket was launched. For F, why are there 2 answers for part E but only 1 practical answer for part D? Well, already underlined here in green, you can see that x equals negative 0.74 is not going to be in the practical domain. So when this rocket is launched, it starts off at 180 feet. It hits 250 feet on the way up and on the way down, creating 2 different answers. But it only hits 100 feet on the way down because it's starting off higher than 180 feet. So I'm going to say that the reason why there's 2 answers for part E but only 1 practical answer for part D is because the negative 0.74 is not in the practical domain. Alright, what are the x-intercepts of this function and what do they mean in the context of this problem? Well, to find the x-intercepts, I'm just going to look on the graph because they're already marked. So the x-intercepts are negative 1.5 and 7.5. And if I didn't have them marked on the graph, or they weren't easy to see from the graph, then I would just solve the equation 0 equals negative 16x squared plus 96x plus 180. So I'd use the quadratic formula and that would get me right to the answer. But I already have them, so we can go ahead and explain what they mean in the context. Well, this first one right here, this x equals negative 1.5, it actually doesn't mean anything in the context. It's not in the practical domain. So it's an extraneous solution here because it's not going to give us anything for our problem. But the 7.5, that does give us a lot of information about the context. So this 7.5, that is going to be the time that it takes for the rocket to hit the ground. So 7.5 seconds after the rocket is launched, the rocket hits the ground. Alright, what are the intervals of increase and decrease in the practical domain, and what do they mean in the context of the problem? Alright, so intervals of increase and decrease in the practical domain. So if we are increasing in the practical domain, we start off at x equals 0 and it increases until x is 3. So this is when the rocket is rising. So it goes between when x is between 0 and 3, and x here is representing the time. And then decrease would be from 3 to 7.5. So decrease, we have when x is between 3 and 7.5. So this is increasing when the rocket is going up in the air, so its altitude is increasing, and then decreasing after the rocket has reached its maximum and it's headed towards the ground. Alright, now is the time for you to pause the video and complete the independent practice. Once you've completed the independent practice, then press play and check your answers. And here are your answers to the independent practice.